Let me remind you where we were last time. We had defined non-deterministic time, non-deterministic polynomial time. So this is a polynomial function of n where the exponent is k. And this is a set of languages. This is the set of all languages which can be decided, where each language in that set can be decided by some non-deterministic Turing machine whose worst case running time is bounded by a polynomial function. So I'm not going to write all that out again because that's exactly what we did last time and we did it in detail. And then I defined NP, that's the union over K of all of these sets. So this is a big set of languages. So a language is an NP if there exists a non-deterministic polynomial Turing machine that can decide it in some polynomial time. So here there was a specific K, and this is a union over K. So here's K specific, and here's the union over all possible K. All right, any questions about that? I know this is fairly abstract, but we did this last time and in some detail. All right, and we also defined P, of course, earlier. P is equal to the, we had defined time, n to the k, that's polynomial deterministic time. So this is a set of languages. This is the set of languages that can be decided by a deterministic Turing machine whose running time is bounded by n to the k. Okay? And then we similarly had P is equal to the union of k time n to the k. Okay? So again, this is defining, just repeating what we did last time. And then P, this is actually a theorem. And the proof is trivial, obvious now, just from the definitions, because we know that every deterministic Turing machine can be viewed as a non-deterministic Turing machine. So if you have a deterministic Turing machine that can decide a language in polynomial time, you certainly have a non-deterministic Turing machine that can decide that language in polynomial time. So P is contained in NP. And I just point that out because, well, it's an important thing to know, but in CS 122, the algorithms course, we also discuss NP, P and NP-completeness. But in that framework, in that class, we can't actually prove this, not prove it correctly. We kind of hand wave it. And I'm pointing out now that because we now understand what a Turing machine really is, and what time bounds for Turing machines really mean, then this is a triviality. Whereas in class 122, we don't have a clean definition of a Turing machine, never even actually use those terms. Okay, so this is the definition of NP, and I also mentioned last time that for a language to be an NP is no great distinction. For a language to be in P is a much more restrictive condition in practice, but we don't know. We don't know actually whether NP is contained in P. That's a big open question, and if NP is contained in P, that would imply that P equals NP. Okay, because we already have this direction. Okay, so this is a big open question: is P equals NP? Does P equal NP? And I think that's about where we stopped last time. But I didn't really get to the point of why this is an important question. Just technically, you should see this as a question now that we have all these definitions. And so I want to go back and clean up one thing, or at least to do one thing that the book does actually before. The book does this before it defines this version of NP. It defines a different version of NP, which is it's commonly used. I don't think it really is necessary in this, but since it's in the book and it's commonly used, let me define this. A verifier for a language A is a Turing machine. Actually, Well, that's funny. He writes algorithm here, but we don't know what the only thing we know about an algorithm in this book, in this course, is an algorithm is something that can be implemented on a Turing machine, right? So I'm going to say Turing machine. Where A equals W such that Turing machine, they call it V. V accepts WC for some string C. Okay, so what is this saying? Normally, when we want to decide a language, input to that Turing machine are strings which may or may not be in that language. And then the Turing machine says accept, yes, that means it's in the language, or reject, that means it's not in the language. Okay? But a verifier actually gets an additional hint or help. A verifier gets this additional string C. And we'll talk a little bit about where C comes from, but in the definition, you don't need to know where C comes from. It's just something that helps the Turing machine come to an accepting conclusion when, just this definition. The set of W that it accepts along with C is exactly equal to the language A. So the picture looks like this. Here's our verifier, and in comes W, and in comes C, and then we accept, or we could reject or not even terminate, but accept if we accept, what are we accepting? We're accepting W C, if and only if W is contained in A. Okay? So the set of these things which V accepts is exactly, it accepts W and C if and only if W is in A. So it's never going to accept if W is not in A, and it should accept if W is in A. But what is this C? This C is something called a hint, or sometimes it's called a certificate. What other words do they use for this? Proof, and so on. So a verifier, it's easier to have a verifier than to have a Turing machine that decides. Okay, so a decider for A that's a more difficult thing to get your hands on than a verifier, because a verifier gets this extra hint. It gets this extra piece of information which can help V accept if and only if W is in A. Okay? And it's even weaker than that because we only have this condition on accept. We don't actually even require that it rejects when W is not in A. Okay? So let me ask you the following question. If there is a decider for A, is there a verifier for A? I hear, what? I hear a yes. Did I hear a no out there? Yes, definitely, because to be a verifier here, I can build a verifier if I have a decider. What should I do? Okay, I'm going to turn this decider into a verifier in the following way. C equals 1. I'm just going to enter or actually, let me just make it more sensible. C is the empty string. Okay? That's not the empty string, that's the empty language. C is the empty string, epsilon. Okay? So I input W, I input the empty string, all right? And then the decider here looks at W and accepts or rejects. And let's put a bigger box here. So this one takes in W. And accepts or rejects based on looking at W. Okay? And then if it accepts, if the decider accepts W, then the verifier accepts WC. Okay? So I've turned this decider into a verifier. It satisfies the definition. The definition says a verifier for a language A is a Turing machine V, where A is the set of strings W such that V accepts WC for some string C. In this case, the C is a trivial one. It's just the empty string, which basically means we don't even need that hint. If you have a decider, it can take in any string W and already decide whether W is an A or not. So it doesn't need any extra help. But for some problems, extra help is helpful, particularly when we add in the notion of time, which is what we're going to do now. Okay. The definition of polynomial time verifier has worst case running time of order n to the k for some k, where n is the size of the input. So n denotes the size of the input W. And it's only W. We don't care about the length of C. However, since the verifier can only run in polynomial time, if C is bigger than a polynomial, if the C is, well, it's not grammatical when I say this, but C is bigger than a polynomial bound on W, then the verifier doesn't even have enough time to look at all of C. So we could add the additional requirement here that the length of C be bounded by a polynomial function of W. Okay? So then we have this definition NP is the class of languages that have polynomial time verifiers. Okay. So it does help, well, because in practice, as it said, the world right now looks like this. We have a huge set of problems, a huge set of languages that we know are in NP, and we have a small set of languages that we know are in P. But we don't know whether these two, and we know that NP contains P. We don't know whether these two sets are the same or not. That's the P equals NP question. Okay, and this says NP is the class of languages that have polynomial time verifiers, and we know that P is the set of languages that have polynomial time deciders. Okay, so it's easier to have a polynomial time verifier than to have a polynomial time decider. A verifier looks a lot like a decider, except that you have this extra hint. You have this hint or proof or certificate. And that sort of suggests the word verifier. Verifier is intuitively verifying that some particular solution is correct. Well, that's the vague way that people talk about these verifiers, and but I don't like it at all, because it's not really getting at the pure technical this is the pure technical definition, but to say that the verifier is somehow checking a proposed solution it's the way we talk about it in CS 122, but it's not rigorous, and what we're doing now is rigorous and correct. Okay, so we have these two different definitions of NP. This one, which personally I think is the most meaningful one, and then this other definition here, NP is a class of languages that have polynomial time verifiers. And of course you'd like to be sure that those two definitions are really defining the same thing, okay, because they sound very different. And so let me give you a proof. And hopefully through the proof, you'll also see a little bit about what this mysterious C is or can be. And then we'll look at some, at least one example to try to make that clearer. Okay. This is theorem. And by the way, in your last homework, which I posted a couple days ago, it also tells you what particular pages in the book we're looking at, because we're in chapter 7, but we're skipping some pages between the sections that are relevant. And so a language is in NP well, okay, this is the way he writes it. A language is in NP if and only if it is decided by some polytime non-deterministic Turing machine. Okay, where have you seen this before? The language is an NP if and only if it's decided by some polytime non-deterministic Turing machine. Doesn't that sound familiar? Wait, what is it? It's the way I defined NP. Okay, so the way the book does it, the book defines NP this way, and then proves this thing as a theorem. Okay? What I did, so you'll understand this when you look at the book, I gave this as the definition of NP, and then another definition over there, and then when we prove this, we're essentially proving that the two definitions are the same, right? Okay. So for this proof, we're going to start with that definition, and we're going to prove this theorem. Okay, so go in one direction. Suppose there is a polytime verifier V for language A. Then what I want to prove, I want to show there is a non-deterministic Turing machine that has running time order n to the k, some polynomial, that decides A. Okay? So we suppose that there is this verifier, and it's running, it's a polynomial time verifier, and we want to show that because of that, there is a non-deterministic Turing machine that has running time bounded by a polynomial that decides A. Okay? So what does that Turing machine look like? Let me give it a name. Call it M. So I want to construct M here. And it should be clear in these kinds of proofs, I mean, you should already, your mind should already tell you that this Turing machine M that we're trying to construct will have within it a copy of V. It can use V. We're assuming that there is a V in here, and V can take in a string and a hint, C, and then this runs in polytime. And this is V, and then this accepts well, it accepts WC if and only if W is contained in A. And we'll have to put a reject out here too, because this is M is going to be a decider, so M has to be able to reject as well as accept. Okay? And so what's going on in here? Well, remember this polytime decider, let's give it, what time does it run in? N to the, let's say L, because I already used K as the exponent on what we want for M. So it runs in some polynomial time bounded by L, N to the L. Okay? All right, well, I mentioned before that the C, the length of C, is also, it better be bounded by N to the L too, or it can be. There's no loss in assuming that it's bounded by that, because the verifier only has N to the L time. That's all it can do. And it has to, you have to clock actually looking at the input C, just as you do when you look at W. So W comes in on a tape, and it takes a step of the Turing machine just to look at every character there. One step for each character, and one step for each character in C as well. So the length of C is bounded by N to the L also. All right? So what does M do? M non-deterministically generates all strings, or if you say each string, this chalk is awful. Each string C of length up to whatever this actual function was. Okay, so this is a polynomial time Turing machine. It's actually, its running time is bounded by some particular polynomial. We're just saying it's that particular polynomial is order N to the L. But there is an actual polynomial. So M can non-deterministically generate each of those strings of length up to that. Now, what does it mean to non-deterministically generate these strings? Okay. Well, deterministically generating them just means some kind of branching structure. So whatever the alphabet is, let's just say it's AB, okay? So, and let's say N is equal to 3 and L is equal to 2, so N to the L is equal to 8, okay? No, not equal to 8. Who let me say that? It's equal to 9. 2 to the third is 8, but 3 squared is 9. Okay. All right. So deterministically generating all C means, well, the first character is either going to be an A or a B, and the second character after that is A or B, A or B, A or B, A or B, A or B. Okay. Yeah, but we'd have to go 9 levels down, right? Okay. 9 levels down. So if I generate all the strings of length N to the L, I'm generating all the strings of length 9, and here's a deterministic tree that shows you how you would do it, right? And so every string that gets generated in here, all the way down to depth 9, that's a string whose size is less than or equal to n to the L. Now, what does it mean non-deterministically to do it? Okay, so we're going to have a Turing machine. So you could imagine a deterministic Turing machine that actually goes along each of these paths and generates all of these actual strings. But now a non-deterministic Turing machine, what does a non-deterministic Turing machine do? It's just one where you build in the transition rules that for the next character on the string, the next character in the string, which is going to be written out on some tape, you could either make it an A or a B. So we could build a non-deterministic Turing machine whose possible computations, each particular computation would be one of these paths through this tree. But it's a non-deterministic Turing machine, so it's not, we don't have to build in the instructions into that Turing machine to actually generate this tree the way we would have to do it if it was a deterministic Turing machine. We just have to say, you're going to generate, this non-deterministic Turing machine is going to generate a string of this length. And the first character is non-deterministically going to be either A or B. And the next character is non-deterministically going to be either A or B. Okay? And it just has to do that the right number of times. So it also has to have some kind of marker to see what the depth is. Everybody, yeah? N is the length of the input, W here. Yeah. Okay, so inside here we have this non-deterministic Turing machine, which is non-deterministically generating, well, its instructions, the instructions of that non-deterministic Turing machine are to non-deterministically generate a string of length n to the L. But its computations are such that any one of those strings could be generated. And having generated that string, it feeds it into the verifier. So it feeds in W, that it came in from here. It feeds in C, and then we have the polynomial-time verifier, okay, which so then we have the polynomial-time verifier, which looks at the W and looks at the C and will accept WC if and only if W is an A. And this polynomial-time verifier, it runs in time-bound n to the L. So if it doesn't accept within that sufficient time bound, then we know we can just reject. Okay. All right. If V, well, actually, no, I don't want to put a clock there. Clocks are really complicated. Okay. What I want to do is just that if when the non-deterministic generator has finished all of the generations of C, if we never had an accept, then in that case we'll reject. Okay, so the C here, how do we want to think about what the C is? The C is really guessing. It's been a guess of all the possible hints that this polynomial-time verifier could use, and then we just we run each one of those. But this whole thing is non-deterministic, and so we've proven what we wanted in that direction. Okay, now in the other direction, if A is decided by a polytime non-deterministic Turing machine, then we want to show that there is a polytime verifier. Okay, now this one is pretty straightforward because what happens is there's a polytime Turing machine that decides. So that means that when you run M on W, there's some computation path that M takes that leads to an accept of M on W where M accepts W. Okay, so this is an accept. And so what the hint is going to be, the hint is just going to be a description of this path. So it says what transition do you do first, what transition do you do second, what transition do you do third, and so on, that leads you from the start state to the accept state in this non-deterministic Turing machine. And then the verifier, what does the verifier look like? The verifier, so this is C, it's the actual path, is the accepting path. And then, again, this is when W is contained in A. And so what's fed into here is C and W. And then the verifier is really just a copy of M. Okay? But it just runs path C specifically. It doesn't have to do anything non-deterministically because it's already been told what is the accepting path of this non-deterministic Turing machine. Okay. And here I've reversed the direction of input and output. But mathematically, that's okay. All right. Well, at any rate, this took longer than I had hoped. But so this shows that those two definitions are the same. Because you'll often hear people talk about verifiers when they talk about NP and NP-completeness. All right. So we know what NP is. It's kind of abstract at this point, but NP equals union K n time n to the K. All right. Let me actually show you one problem that is in NP, so it makes this more concrete. Because we've seen. Let me give you a more concrete one. All right. Clique. So, in a graph, I don't think I've ever defined what a graph is, but here is one. And I think a lot of people just sort of, you've seen graphs before. This is an undirected graph. And a clique is a subset of nodes such that, a subset S, such that every pair of nodes in S is connected by an edge. Okay. So in this particular graph, these three are a clique, these three are a clique, these three are a clique. This pair is a clique. Actually, this pair is also a clique. It's not the largest clique that one is contained in, but it is a clique. This, if I take this 4 nodes, that's not a clique, okay, because this pair of nodes is not connected by an edge, and this is not connected by an edge. If I put in these two, like that, then these 4 nodes now are a clique. Okay? So the clique problem, or the clique language equals, well, the input is going to be a graph and a target K such that there is a clique of size K in G. Okay? So the input to the or the members of this language clique consist of a description of a graph and a particular number K, and that pair is in that language if and only if there's actually a clique of size K inside the graph. So let's take this graph, call it G1. If I have input G1, 3, is that in the language clique? Yes, it is, because this graph G1 has a clique of size 3. Also, G14, the way I've modified it, so it has these edges, that's also in the language clique. What about G15? No, because there is no clique inside here consisting of 5 nodes. Just leave it up to your visual processing to see that. There's no clique of 5 nodes inside here, so this is not in clique. Okay, so we have this language clique, and we can ask whether that language is in NP. Is it contained in NP or not? Okay. Well, we have 2 ways of thinking about this, because we have 2 definitions for NP and they're equivalent. So, do you have a non-deterministic polynomial time decider for clique, or the equivalent way is there a polynomial time verifier? Now, I want to do the verifier way because I think that's the more mysterious, and hopefully this particular specific example will help make concrete what this hint is. So in to the verifier comes the input G and K, and that's what the W is, what we've been saying is W, and also some C. And this has to run in polynomial time, order n to the k time, and this accepts its input, which is gk, if and only if gkc. So it accepts gk c if and only if gk is in clique. But what is this C? Anybody think of, yeah?
Is it like the list of vertices that are make up a size K clique in G?
Yeah, that's a very natural hint, and so C could be a set of K nodes of G that form a clique. in G. So if you give this string, which is it's a description of a set, okay, because this is always a string, but okay, it's a description of a set of, or a list of a set of k nodes in G that form a clique in G, then all the verifier has to be is a Turing machine that just looks at every pair of nodes in the set C and checks whether or not that pair of nodes really is adjacent. Is there an edge between them? Well, in here we have a description of G. Now, I haven't talked about how do we describe a graph so that you can give that description to a Turing machine, but I'll leave that up to you. You can certainly invent ways of turning a description of a graph into a string. So in comes the description of the graph and k, and all the verifier has to do is look at this list of k nodes and verify that every pair of those nodes in the list is in fact adjacent by an edge, connected by an edge in G. So that verification, we only have k nodes here. It's going to look at every pair of nodes. That's bounded by k squared, okay? And k is bounded by n, so the size of the graph. So that's bounded by n squared. So this work in here is certainly bounded by a polynomial function. I have too many k's. This is running time. This k came from this k. So I'm just saying this is a rather trivial. It's trivial to show that this is in NP because there's this very natural hint, which is in fact a proposed or a claimed set of nodes, which is a clique. Well, now where does this hint come from? What people usually worry about when you first see this is, well, but where did you figure out? How did you know? I don't mean me in terms of the answer here, but how does this Turing machine know to get this? And that's not part of the definition. We don't care how difficult it is to find such a string. We don't care how magical you have to be in order to have the right string in there, the right hint. This is a verifier is a machine that's getting a lot of help. It's getting a lot of help because it already knows, in this kind of case, what the answer is. It already knows a set of nodes that forms a clique of the appropriate size. And all it has to do is check that that's the right solution. So another way that you might hear about this distinction between P and NP is that P is the set of languages where you have to have a Turing machine that really can come up with the right answer, accept or reject. Whereas NP is just the set of languages where you have to have a Turing machine that can just verify the right answer. Okay? Verify along with some hint that it should be accept. And again, that's the kind of hand-waving terminology that's used. But this is the actual, what I've been doing today is the actual formal definition. So there exists some hint. But most of the time, the hint is a very, very natural thing. The hint is really just, here's the object, in this case a set of k nodes. Here's an object which proves that, yes, indeed, there is a clique of size k. And all the verifier has to do is check it. And this should be intuitive that when you're trying to solve a problem versus verifying that the solution somebody proposes is right, verifying that the solution is right is an easier task than solving the problem in the first place. So that's what this theory is sort of getting at, but in a very particular formal way. So P is the set of languages where you really know how, there is some polynomial-time Turing machine that really knows how to accept or reject. And NP is a set of languages where there's a polynomial-time Turing machine that knows how to verify that a particular computation is correct, or a particular, now I'm doing that vague hand-waving thing, a particular solution is correct. Okay. All right. P and NP. Now, the most important definition in this whole business, and again, now that I've discussed this a few times now, I hope people can see that for a language to be an NP is no great distinction. You know, it's like getting those plastic pilot wings at the bottom of a Cracker Jacks box. Okay, that doesn't make you a pilot. All right. So, at any rate, it's easy to get those plastic wings, but to get the real ones is harder. So, NP is no great distinction. For a language to be in P is a more difficult thing. All right. Now, last time we talked about polynomial time reductions, polytime reduction. And we know a lot about reductions because we talked about reductions when we talked about undecidability. So we have a language A and a language B, and here's a decider for B, and we want a Turing machine that can decide A. So input is W, and then we do some reduction here of W that created an input W prime, and then based on whether this was accept or reject, accept, reject, then we would accept or reject. And let me just draw this going across, but we saw examples where they had to go that way. But this is what a reduction means. A reduces to B, means that whenever you want to solve a problem of whether W is contained in A, you can feed that W into a larger machine here, which does something on W, creating a W prime, and then it feeds it into the supposed decider for B, and then based on what B does, based on this decider, then accepts or rejects appropriately for whether W is an A. Okay, this is the same picture we did when we were talking about undecidability and decidability. And we said if A reduces to B, now this is some notation we hadn't used before, reduces to B, and B is decidable, then A is decidable. Okay? And flipping that around, if A reduces to B and A is undecidable, then B is undecidable. Okay? Hope everybody remembers that and this makes sense. All right, but now we're going to add on time, because this whole theory of complexity, the complexity theory as opposed to undecidability theory, is about efficiency, whether you can get an efficient Turing machine to do various things. So here, this reduction, this has got to be done by computation by a Turing machine whose work inside here is bounded by a polynomial. The work time is bounded by a polynomial in the length of W. So reduction of W to W prime, and that part of it runs in order, and the length of W is equal to n, n to the k for some k. Okay? So this is the amount of time that you can use to do this reduction. This is a Turing machine inside here. It's a deterministic Turing machine inside here, which is doing this reduction. It's taking W and creating a W prime. But the amount of time it can take to do that has got to be bounded by some n to the k by n to the k for some k. Okay? K is a fixed number, so this is a particular polynomial bound. Okay. So definition: A is polytime reducible to B if A is reducible to B and the reduction, the time for the reduction is bounded by order n to the k for some fixed k. Okay? So this is just saying, this definition is just defining really what it means to be polynomial time reducible. It means this picture. Okay? And the way, is it a question? No. And the way that's written as this A is polytime reducible to B. We put a little p here. All right? So now I can modify some of these. If A is polynomially time reducible to B, and B is polytime decidable, okay, there's some polynomial time bounded Turing machine that decides language B, then A is polytime decidable. Okay? So all I've done is really add the element of time here. We already had this kind of logical relation for decidability, but now we're saying, well, if A can reduce to B in polynomial time, and B itself is polynomial time reducible, then A is polynomial time decidable. Why? Because here this reduction takes some polynomial time, and here this this decider is taking polynomial time as a function of its input. So what is this taking altogether in terms of W? It's a polynomial of a polynomial. Let's say this is n to the k, and this, in terms of its input size, runs an n to the L, where now n is its input size. And so what's the time bound for the decider for A? So the decider for A uses at most n to the k for the reduction. It produces a W prime, which goes into the decider for B. Well, if this reduction takes at most order n to the k time, how big is W prime? It can't be any bigger than the time that was needed to produce it. Okay, so the size of W prime is at most n to the k, and it then takes its input size to the L. So this is n to the k to the L, which is nkl, which is still a polynomial. Okay, k and l are constant numbers, so n to the kl is a polynomial function of this input size. Okay, so that was that. And then if A is polynomial time reducible to B and A is not NP, I'm just abbreviating now what it means. I could have said here if A is reducible to B and B is in P, then A is in P. B is in P, then A is in P, okay, because that's what P means. So if A is polynomial time reducible to B and A is not in P, then what do we have? Well, A reduces in polynomial time to B, but A is not polynomial time decidable. So B can't be polynomial decidable, or otherwise that would, you'd have a way of doing a polynomial time, you would have a way to polynomial time decide A. So this is the same logic as we had before, but now we've put in time. I know I'm going very fast, speaking of time, because we don't have much, and I've got to really get to the punchline of this lecture and one of the ones in the course. Okay, so this is reduction. Now, main definition of this lecture: a language A is NP-complete if and only if two things. First of all, A is an NP, no great distinction. But secondly, the most important one is any, for any language L in NP, L reduces in polynomial time to A. Okay? So a language is NP-complete. To be NP-complete, first of all, it has got to be in NP. And secondly, it's saying whatever other language, whatever other language in NP, for any other language in NP, you can reduce questions of deciding L to the question of deciding A. This is and the reduction is polynomial time. Okay? L reduces to A. It means if when you have a decider here for A, if you have a decider for A, you can build on top of it, and A is NP-complete. You can build on top of this decider a decider for any other language in NP. Because for any other language L in NP, L reduces in polynomial time to A. And so if this is a decider that runs in polynomial time, that is if A is in this class P, then when you build on top of this a polynomial time reduction, or use this in conjunction with a polynomial time reduction of L to A, then you can decide L in polynomial time just by first doing the polynomial time reduction and then running decider A in polynomial time. And a polynomial of a polynomial is still a polynomial. So we have that conclusion. So these NP-complete problems are very expressive. They, in the following way, that every other language in NP can reduce to that language, and in fact, it can reduce it in polynomial time. And so we have the following conclusion that comes from just turning this thing around. If well, we have several conclusions, yeah. If A is NP-complete and A is contained in P, then NP is contained in P. So P equals NP. Okay, this is a theorem. It's a theorem based on just these definitions. If you have a single language, A, that's NP-complete, and NP-complete means that any other language in NP can reduce to it in polynomial time, and that language A happens to be decidable in polynomial time, then any language in NP is decidable in polynomial time. Again, by this kind of construction, by just using the reduction. L is some language in NP, and you use the reduction that reduces L to A in polynomial time. And if A is in P, there's a polynomial time decider for A, and so you hook that up to the reducer. The reducer does its work in polynomial time, sends an input over to the decider. Decider runs in polynomial time. The composition of those two polynomials is still a polynomial, and therefore we have this result that any language in NP would then be in P. And we'd have P contained in NP, and since we already know the opposite, we would then have P equals NP. Okay? So this leads to the belief, since being an NP is no big deal, NP is just really the languages, to be an NP just means that, well, it means what we said over here, but the hand-waving thing, which I keep saying I don't like, is that NP is the set of languages where a proposed solution can be verified in polynomial time, whereas P is the set of languages where you really have to have a deterministic Turing machine that can decide that language in polynomial time. A much, much harder requirement. And so the belief is that no NP-complete language is in P. Because the belief is that P is not equal to NP. But this is still an open question, not been proven, and there's $1 million bounty on its head for anybody who can prove one way or the other. Okay? All right. Let's get to the next point about this, is that how do I prove that additional problems are NP-complete? If A is known to be NP-complete, if A is known to be NP-complete and B is contained in NP, well, let me just skip that part of it. If we want to show that B is NP-complete, we can do that by showing a polytime reduction of to okay, the logic here is identical to the logic of what we were doing when we were talking about proving undecidability. If we have one language which is known to be undecidable, and we want to prove that another language is undecidable, we can do that through the mechanism of reduction. But you've got to be clear on which language reduces to which in order to get that done. Now, playing the role of undecidable is NP-complete. So undecidable was bad, right? We wanted languages to be decidable. Now we have this other thing called NP-complete. Okay? NP-complete is bad in a sense because here we have this belief that no NP-complete language is in P. P is good. Okay? If no NP-complete language is in P, then that's a bad thing. So at any rate, what do we fill in here? We want to show that B is NP-complete. We already know that A is NP-complete. We reduce which language to which language? Yeah. Yeah, A to B. The known NP-complete language has to reduce to the language that we want to show is NP-complete. And the logic of this is, well, is this. It's all, all these things are basically the same thing, and you just have to convince yourself of this structure of this particular statement, And so this is how in practice, we prove that problems are NP-complete. Except for one issue. What is it? Yeah, chicken and egg. You've got to have an NP-complete problem in the first place. You've got to have this A that's known to be NP-complete. And this is the great theorem of this topic, and great shame that I only have 10 minutes left, because if I'd had another 2 or 3 hours, which meant another couple of lectures, I could actually prove to you the existence of an NP-complete problem. And the book does it. It takes about 3 or 4 pages. It's not that hard conceptually. It's just a little bit of detail. So, theorem, there really are NP-complete problems. This isn't just some, all just words and definitions. And the one that the book proves, and historically is the first one that was established, where the book proves that the problem is NP-complete from scratch, is this problem SAT. And SAT is, in SAT you have a number of clauses. So inside a clause, you have literals, which are connected by ORs. Now, this is an OR. X1 or X2 or X3 not, or X3 bar. And then an AND. So these are ORs. This is AND. X1 or X3 or X7, or something like that. Anyway, a whole series of these clauses that are connected by ands. And to make this expression true, you have to come up with assignments of truth or false to the variables. But if you assign X3 bar to be true, you have to make X3 false. So the bar is a not. Okay? So these are just Boolean variables. I'm sure everybody's seen some things like this before. Boolean variables, and if you can assign the variables to be true and false, obeying this rule, the rule is that whenever a literal is assigned to be true, its complement, or the bar version of it, has to be false. So it's satisfiable if and only if truth values can be assigned to make it true. These are connected by and, so this has got to be made true, and this has got to be made true, and all the clauses have got to be made true. And this is a problem which is an NP. What's the hint? What kind of a hint would you have in this problem? It would just be, this is going to be true, this is going to be false, and so on. And then the verifier, all the verifier has to do is make sure that inside each clause there's at least one of these literals that's true. Okay? So it's very simple to see that SAT is an NP. Is SAT in P? Well, the only kind of algorithms that you'd likely think of are brute force enumeration of all the possible truth and false settings for the variables, and that's not a polynomial time. The number of those settings can grow exponentially in the size of the input and not bounded by a polynomial. Now, I know I'm going very, very fast here, but this is the central logic of once we know that there's an NP-complete problem, then you can prove additional problems are NP-complete using this logic. Now, what's on your homework asks you, well, first of all, it just gives you a particular formula here, expression, and asks you whether that's satisfiable. That's just to make sure you really are understanding what this means. And then it asks you to prove certain problems are NP-complete by using this logic. And you'll see examples in the book of how you do such reductions. I'll do one very, very quick one. Assuming that we know SAT is NP-complete, so SAT is NP-complete, show that clique is NP-complete. Okay? If A is known to be NP-complete, I want to show that B is NP. We also have to show here, by the way, that B is contained in NP. That's the trivial part of the proof when you want to do that, show a new problem is NP-complete. SAT is NP-complete. We want to show that clique is NP-complete, so we want to reduce SAT in polynomial time to clique. So the input here is a Boolean expression. The input here is a graph and some target. And, well, there's one other piece of business I have to do today. We only have 4 minutes left. So it's in the book, and I'll leave that to you. And I really apologize for how this got compressed. I would have loved to have given you the full proof that SAT itself is NP-complete. It's also in the book. It's not that terrible. Don't leave.